Lesson 7.6 is on exponential functions, and this is on page 453 in your book. So basically, what this boils down to, exponential functions, is we have functions where we have a variable in the exponent. And for you guys at this point, usually x is going to be the variable in the exponent. Okay, so this is what we're looking at here, exponential function. So it's y equals a times b to the x power. So you can see what the graphs look like in the box there. Just some examples. Some examples of exponential functions. We could have like y equals 5 to the x power. That would be an exponential function. Y equals 2 times 3/5 to the x power would be an exponential function, okay, because we have an x in our exponent. And I've got a note to remind myself here. Horizontal asymptotes. When we graph exponential functions, there's kind of like an imaginary line, a horizontal imaginary line that the graphs don't cross is generally how these work, okay? So it's kind of like, if you can imagine, just for an analogy that you can maybe relate to, if you've seen something with a dog, or if you have a dog and you've got an electric fence. So the dog might get kind of close to that electric fence. It's probably not going to cross over that electric fence to get shocked, okay? So that's kind of the idea here. So we've got, like, if you look at this graph here, this graph, actually, both of these graphs are getting very close to the x-axis, y equals 0. Okay, they're getting close to that line, but they're not going to cross that. The reason being is that x, we have 1/2 to some power of x. As x is getting really big, if you take a half times itself a bunch of times, the more times you take half of something, the smaller it's getting. But it's still going to say a positive number, right? Okay, half times half is a fourth, times a half is an eighth, times a half is a 16th, times a half is 1/32. And it gets smaller and smaller, but it's never going to get to 0. That's the idea of that horizontal asymptote. And like I said here, we're going to talk more about those in Chapter 11. So don't worry about it too much, but as far as when you graph your equations, that's going to be what you'll see. So on the next page, it says, suppose all the x values in the table have a common difference. If all the y values have a common difference, the table represents a linear function. So if all the x values have a common difference, and then if the y values have a common difference, then it's a linear function. If the y values have a common ratio, then it represents an exponential function. Okay? So common difference on the x's, common differences on the y's, it's a linear function. Common difference on the x, but a common ratio on the y's, then it's exponential. So we'll see what that means as we go through this. So if you look at problem 1, part A, they're looking for a pattern here. So pattern, x's are going up by 1s, y's are not going up or down by the same number each time. But there's a pattern. They're being multiplied by 3 each time. That means we have a common ratio. And so that means that this would be an exponential function. That graph would be an exponential function. If you're not sure, okay, you're asked a question about what it is and you're not sure what it is, your backup plan, graph the points. Okay, take some graph paper, graph the points and see what it looks like. Well, that's nowhere near a straight line. Oh yeah, that's an exponential function. Okay, So in other words, they're giving you an idea, a way that you can quickly figure out the answers to these. But if you forget, graph it, see what it looks like. You'll be fine. Okay? Part B, they're just giving us an equation, y equals 3x. That's a linear function. You guys know, anytime if you see something like y equals mx plus b, anytime you've got y and an x and you don't have, a variable as an exponent or a variable in the denominator or anything like that, it's going to be a linear function. Okay? So that one, you could plot some points, make an XY chart, plot some points, but that's going to be a straight line, slope of 3. Okay, so let's look at the got it 1, and basically we're doing the same thing here. So first of all, on our table, they're asking if this is linear or exponential. So on part A, you can see the x's are going up by 1 each time. And then the question is on the y's, are they adding or subtracting by something, or are they multiplying or dividing by something? Well, what happens, and if you want to start, if you want to start going from 1 to 3 and then back up, negative 1 to 1, a little bit more of a challenge. But anyway, you can see on the y's they're adding 2 each time. So if you guys remember, we talked about slope is a change in y and change in x, change in y over change in x. We have the same change in y over change in x every time, which means we have a constant slope. If we have a constant slope, we have a straight line. So this would be linear because it's a straight line. Part B, they've given you an equation. So equation, again, you can make a table if you want, substitute numbers in for x and see what kind of points you get, graph your points and see, do they make a straight line or do they not make a straight line, is basically the options here. Otherwise, if you just look at the form of it and think about what we talked about with linear equations a minute ago, that might do the job also. So this one is going to be exponential, and kind of your cue that's going to give this away is we have a variable in the exponential, okay? So again, like I said, you could make a table if you put in 0. Now remember, 6 to the 0 power is actually equal to 1. 3 times 1 is 3. We put a 1 in. We got 6 to the first, so 6 times 3 is 18. We could do a 2. 6 squared is 36. 36 times 3, I don't know, 108. Okay, so you can probably tell by that, and if not, you could try and graph it. That thing's going up really quick. Okay, it is nowhere even close to being a straight line. So exponential. So problem 2, talking about population growth. Suppose 30 flower beetles are left undisturbed in a warehouse bin. The beetle population doubles each week. Function f of x equals 30 times 2 to the x power gives the population after x weeks. How many beetles will there be after 56 days? Be careful on this. Population after x weeks. This is saying after 56 days. So 56 days, if you do 56 divided by 7, which we should probably show that so we don't just magically pull a number out of nowhere. So that's 8 weeks, and then that's why they substituted an 8 in place of x. Remember, order of operations, we would do exponents before we multiply. So if we weren't allowed to use a calculator, we have to understand what steps we need to do. 2 to the 8th power, we multiply all those 2's together, we get 256. 30 times 256, we now have 7,680 beetles. Okay, it's getting out of control. So similar idea, we got it too. Rabbits, always rabbits. Initial population of 20 rabbits, triples every half year. So here's our function, and that's the population after X half-year periods. And the question is, how many rabbits will there be after 3 years? Okay, so once again, we have to watch this because they're talking about half-year periods. So in 3 years, we're looking how many half-year periods do we have. We would have 6 half-year periods. And, you know, if that doesn't make sense why we would do that, just think 3 divided by a half. We're dividing 3 years up into half years, basically. Keep change reciprocal, you'll get this, which will be 6. So 6 half years. And then now we can substitute that into our formula. Remember that function notation we talked about, f of x, is instead of just putting a y there. So we could say f of 6. In other words, if I put a 6 in place of x, what am I going to get for y is the question. And remember, the f of 6, we don't do anything with that. So if you do this, so 3 to the 6th power 729, again, doing the exponents before we multiply. And then if you multiply, that would be 14,580, okay? And when you guys do these, once you get to this point, I mean, you can use your calculator to get to that answer. I'm just making sure you understand order of operations, what you would do if you were doing it by hand. We got to make sure we remember how to do that stuff because we can't always use a calculator. So 14,580 rabbits we would have from the original 20. Again, it's kind of getting out of control here. Problem 3, they're asking us to graph an exponential function. When we graph a line, we talked about, 2 points make a line. We'll do a third point just to be safe. When you're graphing an exponential function, you probably want to pick 5 points like the book's doing. Because this thing is not going in a straight line, we have to keep putting points so we can have a better idea of where it's actually going. So like the book did, probably a good idea, pick a couple negative points, 0, and a couple of positive points. If you want to just pick these same 5 points every time, that's fine. Okay, kind of like we did 0, 1, and 2 when we graphed a line. -2, -1, 0, 1, and 2. So they just substituted in, and then they worked it out. They got their y values, and then these are the points then. So if they put -2 in, they got 3/4. So there's our coordinates of 1 point. And then they just went and graphed those points. I know some of those points aren't really nice. Just graph them the best you can, and if you're pretty close to it, like -2 and 3/4. 3/4 is a little difficult to graph, but we can be close on that. And then that's what the graph looks like. And like I said, the book's not really showing this too well here, but this graph actually is going to, continue. It could continue over to the left, and it would just keep being very close to that x-axis, but it's not going to cross it. Okay, and that's what your graph's going to look like. It's either going to be this way or it's going to be coming down the other way, just based off of the things it mentioned at the beginning, whether that number in front is positive and things like that. Okay, so 5 points though in order to graph this. So let's try for variety. Let's look at part B. Got it, part B. So if you want to do a working column in the middle of your table, you can. Like they did in the book here, if you want to go -2 up to 2. and substitute in. Okay. And again, technically, we could work these out by hand. Negative 0.5 is the same as negative a half. 3 to the negative second power is 1 over 3 to the second power. And 3 to the second power is 9. 2 times 9 is 18. So that would be negative 1/18. If you want to get something that's not a decimal for your answer there, you could do it on the calculator, but it's going to be a not very nice decimal if you do it that way, just so you know. Same idea here. We put a negative 1 in. 3 to the negative first, that's like 1/3. 1 over 3 to the first power, or 1/3. So that'd be negative 1/6. And we put in a 0. Well, 3 to the 0 power is equal to 1, so that'd be negative 0.5, or negative 1/2. If you put a 1 in, three to the first power is just the same as 3. So that'd be negative 1/2 times 3, be negative 3/2, so negative 1.5. And if we put a 2 in, so 3 squared would be 9. So that'd be negative 9/2, which would be like negative 4.5. Okay, so you can see we actually started off just under the x-axis and then we're going away from it. So if we were graphing these points, negative 2, and we're just barely negative. I mean, this is really difficult to draw. Negative 1, and we're just still right there almost. 0, we're at negative 1/2. 1, we're at negative 1.5. 2, we're at negative 4.5. And so when you draw these, they'll kind of have a curve to them, okay? And like I said, over to the left, it's going to stay really close to the x-axis, but it's not going to cross over it. So problem 4, computer mapping software allows you to zoom in on an area to view it in more detail. Okay, kind of like what we just did here. Function f of x equals 100 times 2500ths to the x power models the percent of the original area the map shows after zooming in x times. Graph the function. So you can see 0, if you put a 0 in, 0.25 to the 0 is equal to 1. And there we are, it's 100%. We zoomed in 0 times, we're at 100%. Zoom in 1 time, work that out, you get 25. So 1 time zooming in, we can now just see 25% of what we could originally. Okay, 2 times we can see 6.25% and so on. And you can see by the 4th time, we can't even see 0.5% of what we started with. So there's the graph. And again, you know, we could connect those dots to kind of show what that's doing. And then if you look at the got at 4a, it says you can also zoom out to view a larger area. Function f of x equals 100 times 4 to the x models the percent of the original area the map shows. So when you zoom out, Okay, zoom out, then you can see more. So one difference on this, if this is our function, we talked about using -2, -1, 0, 1, and 2. What's the least number of times we can zoom out? 0. Okay, we cannot zoom out a negative number of times. So we got to start with 0 here, okay? So we start with 0, 1, 2. We can go 0 up to 4 if you want, okay? So I did not put my working column in the middle here, which, you know, that's your decision if you want to do that or not. 4 to the 0 power equals 1. So here we are again. If we don't zoom in any times, we're still seeing 100%. Or zoom out, rather. Zoom out, sorry. If we zoom out one time, that'd be 100 times 4. So now we could see 400% of what we could originally. If we zoom out 2 times, we can see 1,600%, okay, and so on. And, you know, it gets to a point with this, like, you know, how am I going to even graph that? Because these numbers are getting so big. I would go by hundreds, okay, just graph it going by hundreds. And I don't even know, honestly, you know, once you get to a point, do you even need to go much further than that to tell? I mean, we could do one more, I guess, but that's 6,400. So, you know, how much time do I want to spend graphing this thing is kind of the question at that point. So again, it's, you know, 0, 100. If I'm going by hundreds, just to sketch it out. Okay, I should be writing other numbers in here, but there we are, and there we are, and there we are. Okay, and so kind of what's going to happen, we've talked about it before with parabolas, is like either a U or an upside down U. This is kind of going to be like half of one of those, is kind of what we're looking at. Okay, it's kind of like half of a parabola if you think about it in those terms, except for, you know, over to the left, this would go close to the x-axis, but again, we can't zoom out negative times, so those numbers don't make sense. So we'll just stay in the first quadrant here. So on the next page, it talks about, on problem 5, what is the solution or solutions of 2 to the x power equals 5/10 x plus 2. So what we can do actually is we can make one of these sides, put that in as y1 in our calculator. The other side we can put in as y2 in the calculator. You'll be learning methods when you get into high school, methods of how you can solve this otherwise, but for now, that's going to be basically our method. So if you graph those, and then remember we can calculate the intersection. And what you'll notice on these is that since that one graph curves, it actually intersects twice. We actually have 2 solutions where these graphs intersect. Okay, so if you look at the Got It 5 part A, again, if you put in y1, if you put in 3/10 to the x power, and y2 you put in 5, graph those, and then calculate the intersection, we can find where these graphs intersect. It's not always going to have two intersection points. It's possible it could only have one intersection point, just depending on how it goes. This one actually is only going to have one intersection point. So that would be a matter of graphing that and then looking on your calculator and checking where that intersects. So these, if you work through that, that would be about negative 1.34 would be the intersection point. In other words, x is about negative 1.34 where they intersect. Okay, and you know, just to try, make sure you try a couple of these. Part B, if you work that, would be negative 45 hundredths. When you're typing these in, try to get an exponent like that. There's a little caret button on your calculator that you'll need to use to make that as an exponent. And depending what calculator you use, some calculators it might actually put it where it looks like a little exponent, and some it might just show it just keeping it this way with some of the older calculators especially. So look at a couple problems on the lesson check just to make sure we got this figured out. So number 1, they want us to evaluate this for x equals 3. So we're just going to put a 3 in place of x. Again, f of x is there just instead of a y. You could technically put a y there. It's just a different way of writing it. When they write it in function notation, technically we could put f of 3, which means we're putting 3 in place of x. And when we do that, we'll do the exponent first. So 2 cubed, 2 times 2 times 2 is 8, and 6 times 8 is 48. Number 2 would be the same idea. W is a negative number here, so we could mention that because it's going to give us a negative exponent. So 3 to the negative second power is like 1 over 3 to the second power. 3 times 3 is 9, so that's like 1/9. And then if you multiply those, that'd be 45/9, and 45 divided by 9 is 5. The graphing, once again, this one, number 4, we don't really know what's going on, so I'm going to assume negative values are okay. And again, it's just substituting in and working it out. So, you know, if we didn't have a calculator, to the negative second power, it'd be like 2 over 1 to the second power, which is just like 2 to the second power, 2 to the second power, 2 times 2 is 4, so that'd be 16. Negative 1, that'd be so like 4 times 2 over 1 to the first power. So 4 times 2 basically, which is 8. And there'll always be a pattern with these exponential ones. If we just keep going up by 1s on our x's every time, there should be a pattern with your y's. So I encourage you to still work through them, but you can look for that pattern to kind of verify you did these correctly. Anything to the 0 power, so half to the 0 power is equal to 1, so 4 times 1 is 4. Okay, in other words, if you notice, each of these is dividing by 2 or multiplying by half, which actually is our base here, you might notice. 4 times a half of 4 is 2, and then This would be 4 times a fourth. So a fourth of 4 would be 1. Okay, and again, all the way through here, we actually divided by 2 every time. Okay, and again, you could graph those points, and you can see kind of just a quick sketch to give you an idea of what that looks like. It's going to look something like that, roughly, for number 4. Number 7, a student evaluated for x equals -1. Describe the student's mistake and correct it. The mistake they did is they multiplied these things together. They multiplied, and these were not like bases. Okay, if it's just 3 times 4 and that's all you got, no exponents, you can multiply. But if you have exponents on something, you can't just multiply those together. So 4 to the negative first power, that'd be like 1 over 4 to the first power, or just 1/4, and multiply, that would be 3/4. Okay, we mentioned with the graphs that we mentioned things that had one solution when we graphed these, like an exponential with a line had one solution or 2 solutions. Just to show you another example, it's possible to have more than 2 solutions. We've got a cubic function, so if you put this left side in as y1, put the right side in as y2, and you graphed it, this actually has 3 solutions. And it kind of has to do with that third power. Third power, this thing's going to turn a couple times on this graph. So it keeps turning back and forth, and it goes above and below the line and keeps weaving in and out. So that's why we have 3 solutions. So this gives you an idea of how to work with exponential functions.